In our previous lecture, in this video lecture series on stability of columns, we looked at the effect of end restraints on the critical buckling load and the critical buckling stress. We are going to continue with that video lecture, and today, before looking at a numerical problem, one thing left to be learned in this chapter is the effective length of columns. So there are other topics also which we can discuss in this chapter. For example, what will be the critical load of a column that is supported in a general way, or what will be the critical load of a column which is acted upon by an eccentric force. So that may be the topics of future discussion, but in today's lecture we will discuss first about the effective length of columns based on the derivation that we have done in our previous videos, and then we will look at a numerical at the end of today's lecture. So let's start with today's. So what we saw in our derivations in our previous two video lectures. First, we looked at the derivation of an ideal column which was pinned at both ends. And in our previous video lecture, we looked at the derivation of critical load for a column with an end fixed and the other end pinned. So if you remember, for this pinned condition, we got the value of critical load is pi square EI over L square, and this is for the primary buckling mode. And for the column with one end fixed and one end pinned, we got the value of critical load to be 20.19 EI over L squared. We saw that the critical load for the second case was almost 105 times the critical load for first case. So what we see by comparing these two formulae is that a change of end conditions leads to an expression of the buckling load that differs from that in the Euler formula only in the value of a multiplicative constant. And that different multiplicative constants, as you can see for these two cases, is pi square in the first case and 20.19 in the second case. If you derive these expressions for other conditions such as one end fixed and the other end free, or both end hinged, or any other support condition, you will see that comparing to the original Euler formula for this ideal column, the expression for buckling load will only differ in respect of this multiplicative constant before EI by L squared. So because these only differ by this multiplicative constant, what we can do is, for any column with an arbitrary end conditions, we can determine the elastic buckling load. So this formula of buckling load, our Euler formula, can be extended to give the elastic buckling load of columns with arbitrary end conditions. If we write it as PCR is given as pi square EI over LE square, where LE is the effective length of the column. Now this LE will be a certain constant factor multiplied with the length of the column. We also have pi square here, remember. So if we separate this, what happens is that we get PCR equals to pi square over K square EI over L square. Now you can see that we have a multiplicative constant pi square over K square here, and the value of this constant is dependent on the arbitrary end conditions. So if we write our formula in this way, in terms of this effective length, then we can derive the elastic buckling load for any column with any type of arbitrary end condition. So how do we define this parameter here, LE? The effective length, or LE, is the length of a pin-ended column having the same buckling load as the actual column. So let us say that the buckling load of our given column, that may be any column, is some value, let's say 400 kilonewton. So what should be the length of a pin-ended column such that it also has the same buckling load, 400 kilonewton? That is given by the effective length of the column. So remember, any column that we have been given, and a column with any arbitrary end condition has a critical buckling load of 400 kilonewton. What should be the length of a pin-ended column such that it has the same buckling load as that of our given column? That is given by the effective length of that column. So this is the definition of the effective length. So we are equating the expression for the critical buckling load for a fixed pinned column to the expression pi square EI over LE square. So this is in terms of effective length here. We know the expression for critical load for a fixed pinned column, which we get is 20.19 EI over LE square. So if you compare these two equations, what you get is that pi square over LE square is equal to 20.19 over LE square. So you can see, if you rearrange the terms and simplify them, the effective length is 0.70 times the total length of the column. If you remember the diagram that we used during our previous lecture for the derivation of this critical buckling load of fixed pin column, what we did there was that, suppose this is one end of our column which is pinned, and this is another end of our column which is fixed. So what was the shape of our primary buckling mode or primary mode shape of our column here? We derived a formula for the elastic mode shape, or you can say the buckling load of our column, and there we got the primary buckling shape was somewhat like this, and there we represented the distance from here to here is about equal to 0.70 L, and that is the same expression that we get here for the effective length of our column, which is 0.70 L. So the effective length of a column, previously we defined it as that length of a column for a pin-ended column which has the same buckling load as for a given column with arbitrary end conditions. Secondly, physically we can also describe the effective length of a column as the distance between points of zero moment, or the distance between the points of contraflexure, that is the point of zero moment, when the column is deflected in its fundamental elastic buckling mode. So when the column is deflected in its fundamental mode, that is first mode shape, at that condition, if we measure the distance between the points of zero moment in a column, then that distance is known as the effective length of that column. So this is the physical definition of effective length. So I have two diagrams here which shows the primary buckling shape or primary mode shape of deflection for different types of column. So basically the value of K, we derive that LE, that is effective length, is some constant times L. We have defined it in this way. So basically this value of K is 1 for pinned column, because if you remember our first definition, the effective length is that length of a pinned column which has the same deflection as that of a given column. So our given column in pinned column is this pinned column itself. So the effective length is equal to the length of this pinned column, so LE equals to L. Whereas for a fixed pinned column, the value of K, or this constant, is 0.7, so that the effective length is equal to 0.7 L. In case of columns with both ends fixed, the value of K is 0.5, such that the effective length is half of the total length of the column. For a partially restrained column, the value of K is between 0.5 and 1. So this 0.5 is the condition for both end fixed column, and 1 is the condition for both end pinned. If our column is partially restrained, then the value of k also lies between 0.5 and 1. And finally, for a column with one end fixed and one end free, the value of k is 2. So the effective length is exactly twice the length of our column. So this image I have taken from Mechanics of Materials by Roy R. Craig. A similar diagram is shown, and this image I have taken from Mechanics of Materials by Gier and Goodnow. It shows the same thing that we saw in our previous slide, except that now the formula has been depicted along with the figure have been given along with the formula. For example, for pin column, this was the value of our critical load. The effective length is equal to the length of the column and k equals to 1. For fixed pinned column, which we derived in our previous lecture, we got 20.19 EI over L squared. And if you want to express this 20.19 in terms of pi square, the constant multiplicative constant will be 2.046 pi square. The effective length is almost 0.7 times L, and the value of k is this constant here. Similarly, for a fixed and free column, this is the value of your PCR and this is the value of your effective length. And finally, for fixed column, the critical buckling load is given by this formula here, and the effective length is 0.5. So you can even compare the value of this critical load and base your comparisons based on the effective length. So if you see here, when the effective length is equal to the length of the column, this is the value of critical load, whereas the effective length, when it is half of the length of the column, this is the value of critical load. So one comparison that you can make is, when the effective length is decreased to half, the critical load here has increased by 4 times. Similarly, if you compare this first and second case here, when the effective length has been doubled, the critical load has been decreased by 4 times. So one general inference that you can make from this is that the larger the effective length of a column, the lesser is the value of its critical load. So out of these 4 cases, you can see that this third case has the lowest value of effective length, so it has the highest value of critical load. Somewhat inverse relationship between the effective length and critical load. Similarly, you can derive the expression for critical buckling stress or elastic buckling stress also. So LE is equivalent to KL. So in the value of PCR, instead of LE, you can write here KL whole square. And if you want to obtain the expression for elastic buckling load, in this formula for slenderness ratio in the denominator, we have used the value of effective length here, KL by R whole square. So KL by R is now the effectiveness or effective slenderness ratio of the compression member. So this brings us to the end of discussion on effective length of columns. At the end of this lecture, now we will discuss a short numerical. We will go through it very fast. It's a practical example of column deflection. And this numerical I have taken from Mechanics of Materials by Gier and Goodnow. So I want to acknowledge them before starting with this numerical problem. So in this numerical problem, you can see here, some people are standing on this platform here. This is a viewing platform. And this platform is supported at this end by a column. This column is supported on a concrete substructure here, and at the top it is supported by this platform here. So what our question says is that a viewing platform in a wild animal park is supported by a row of aluminum pipes having length 3.25 meter and the outer diameter 100 mm. So we have a circular pipe here with length L equals to 3.25 meter and the outer diameter of them 100 mm. The thickness of our circular column we have assumed is T in the diagram here. So the bases of the columns are set in concrete footings and the tops of the columns are supported laterally by the platform. The columns are being designed to support compressive loads of 100 kN. So what we have to do is we have to determine the minimum required thickness T of the columns. If a factor of safety N equals to 3 is required with respect to Euler buckling, and the value that we have been given is 72 gigapascals for the modulus of elasticity and 480 megapascals for the proportional limit. So let us begin with the solution of this problem. So first we have to determine the critical load. So since what the question says is that our column is fixed to a concrete structure at the bottom and laterally supported by a platform at the top, we can approximately assume this column to be fixed pinned column. The column is supposed to be fixed at the base and pinned at the top. So because of the manner in which columns are constructed, we will model this column as fixed pin column. We know the value of critical load for fixed pin column is given by this formula here. Here is the modulus of elasticity, which is given as 72 gigapascals. The length of the column is 3.25 meter, and the value of I. What is the value of I? I is the moment of inertia of the column. Since our column is of a tubular cross section, that is hollow in the middle and it has some thickness T, the value of moment of inertia of that tubular cross section is given by this formula here, pi by 64 into d to the power 4 minus d minus 2t to the power 4. So this is basically the inner diameter. So moment of inertia of our tubular cross section is pi by 64, outer diameter to the power 4 minus inner diameter to the power 4. Since we have thickness on our two sides, we have to subtract 2 times the thickness from this outer diameter to get the value of inner diameter. So the value of outer diameter is 0.1 meter to the power 4. The thickness we have to determine, so we will leave this as T, and this is the value of our moment of inertia. Here T is also expressed in meters, since we have converted the value of D to meters here. Now our critical load, actually the columns have been designed for a load of 100 kilonewton, but a factor of safety has also been given, which is equal to 3 according to the question. So each column has to be designed for a total critical load of this factor of safety multiplied by the 100 kilonewton, which we get as 300 kilonewton. Substitute the value of 300 kilonewton in our previous formula here, which we got as PCR is, let's see the formula here, 2.046 pi square EI over L square. So PCR is 300 kilonewton, which is 300,000 newton, 2.046 pi square. The value of E is 72 gigapascals, so 72 into 10 to the power 9 pascals. The length is 3.25 meters, and the value of I, which is given here. Now solve these equations, rearrange the terms, and finally what you get is 0.1 meter minus 2t to the power 4 is this much meter to the power 4. If you solve this equation, you get the value of thickness is 0.006825, and if you convert it into millimeters, you get the required thickness of our column is 6.83 millimeters. So this is the answer to our problem. But this numerical in this book has some additional calculations also, which I will just read and you can go through it by yourself also. There are some supplementary calculations. What it has done is that, knowing the diameter, which is 0.1 meter, and the thickness of the column, which we determined, we can now calculate its moment of inertia, cross-sectional area, and finally radius of gyration. So use the value of thickness 6.83 mm in this equation here to get the value of moment of inertia. Compute the area of your cross section and use this formula here to get the radius of gyration, which you get is 33 mm. So what it says here is that the slenderness ratio L by R of the column is approximately 98. L is 3.25 meters, so 3250 mm over R is 33 mm. 33 mm, this comes out nearly equal to 98. So this is in the customary range for slender columns, this 98. This you can check by consulting any standard code of practice. And also the diameter to thickness ratio is approximately 15. That means 100 over 6.83. Approximately equal to 15, which should be adequate to prevent local buckling of the walls of the column. So while designing for these compressive columns, it is not only necessary to ensure that there is no overall global buckling, but we also should make sure that we are not using the columns of such thickness such that there are local buckling generated. Because we saw in our formula for critical load is that higher the value of area of cross section, or this higher the value of this moment of inertia, the greater is the critical buckling load. So this higher value of moment of inertia can be acquired by choosing such a cross section of our column such that the bars are distributed away from the center. So in doing so, we see that these tubular cross sections are very much efficient in resisting the compressive loads. However, the thickness of these tubular sections should not be so low such that there induces some local buckling. So you can take the example of a certain can of some juice or some cold drinks. These cans have very small thickness of the wall such that when you press from the top, even the slightest force can cause local buckling in these cans. So we have to make sure that this condition is not present in our structures. And finally, you were given the value of, if you look at this question, you were also given the value of proportional limit for your column, which was 480 megapascals. We also looked at this during our classes that the Euler buckling theory is satisfactory only below the proportional limit. So let us find the critical stress in this aluminum column. We do that by dividing our critical load by the area, which is 300 kilonewton over almost 2000 millimeter square. We get the critical buckling stress is 150 megapascals, which is much less than this proportional limit. Therefore, our calculation for the critical load using Euler buckling theory is satisfactory. So these are some supplementary calculations given for this numerical problem. So this brings us to the end of our today's video lecture. If possible, we will have 1 or 2 more video lectures in this course, and then this course will be completed. So we'll meet again soon in our next lecture. Till then, stay safe and thank you.